Any scientist or lab worker could tell you that scientific equipment is very expensive. Even seemingly simplistic devices such as pH meters could cost hundreds to thousands of dollars, depending on the desired accuracy, of course. So this has had me questioning, first of all, why? And second of all, is it possible for me to design and build some of these devices from scratch for much cheaper, but then also maintaining a high degree of accuracy comparable to these other devices? To test this, I needed a device with a relatively simplistic operation, but also that still had a real-world application, because I would like to use this for other projects as well. What I stumbled upon through just a little bit of research was a device called a colorimeter, which seems to be pretty simplistic in design, but also tends to be very expensive. So let's see just how expensive and just how difficult it really is to build one of these colorimeters from scratch. Before we dig into this project, it may be useful to know what a colorimeter actually is and what this can be used for. Fundamentally speaking, colorimeters are devices that measure the absorbance of particular wavelengths of light by a specific solution. To break this down, there are a few basic parts of this device: the light source, the cuvette that holds the solution, and the photodetector. In its simplest form, the light at a desired wavelength or color is shown through the cuvette holding the sample. The sample itself has been chemically dyed depending on what solute is being measured. The intensity of the dye is proportional to the concentration of the solute. So more solute means you'll have a darker color. Less solute means lighter color. This will affect the amount of light that's absorbed by the solution and transmitted to the photodetector. This principle is an application of the Beer-Lambert law, which states that the concentration of a solute is proportional to the absorbance. Now, the color of the transmitted light is very important. You want to transmit at a wavelength that is complementary to the color of the solution dye. So this can generally be determined by seeing what color is opposite on the color wheel. Colorimeters allow the measurement of a wide range of water solutes, making them a great tool for water quality assessment. The only problem, as I mentioned, is that they are very expensive. Now, considering that colorimeters are specifically designed for measuring the constituents of water or liquid samples, I need to figure out what sample I'm actually going to measure. The first that comes to my mind is the river that I walk by almost weekly. The water in this river is often pretty turbid and typically smells pretty bad. So I figured there's got to be something good, or well, maybe not so good, that could be measured in this river using colorimetry. But before I collect a water sample and think about what constituent I actually want to measure, I need to actually build this device and make sure that it's working properly. The first step of doing this is designing the circuitry. To do this, I used a free open source online program called Tinkercad. Now, Tinkercad has the ability to do circuitry design as well as 3D modeling. For this project, the circuitry is fairly simple, which is part of the reason why I chose it. I'm still fairly inexperienced with electrical engineering, so this gave a great entry point. So I went ahead and sketched this up, and the way this works is pretty simple. So the Arduino Uno is going to control this entire project. To the digital pins, I have my 3 LEDs, so I have a blue, a green, and a red LED. And then to the analog pins, I have my 3 photodetectors. So then all 6 of these components are wired to the grounding rail. So now that I have this designed, I can start thinking about my shopping list. So I know that I need 3 LEDs, I need 3 resistors, I need 3 photodetectors, I need a good bit of wiring to go in between each of these, and then I need my Arduino Uno. So let me go ahead and place this order and wait for these to come.
Tomorrow.
So I just got everything in the mail, so let's go ahead and total this project up so far. So firstly, I have my 3 LEDs, which were 30 cents. I have my 3 resistors, which were 15 cents. I have my 3 photodetectors, which were $4.42. I have my wire, which was free. I was able to scrap this off of some old projects. And then I have my Arduino Uno, which was $16.04. So altogether so far, we have $20.91 for components. So the next step here is to go ahead and get these out, get these wired up, and get some things tested. I started off by soldering the resistors, which are 220 ohms, to the anode leads of the LEDs. Please excuse the terrible solder job here. I am still pretty new at this part as well. Secondly, I soldered the 22 gauge jumper wire to the other end of the resistor. I'll also solder a 22 gauge jumper wire to the cathode lead of the LEDs, which will go to the common ground. The photodiodes are a little simpler. I'll just solder jumper wires to both leads. This does take a bit more caution though, since they are a bit more sensitive to excessive heat, and I did already burn some of these out. Now that the electronics are put together, I can start thinking about and designing the housing that's actually going to contain these components. I was able to do this in Tinkercad for free as well. So what I'm showing here is the first model that I just finished designing. So there's a few key functionalities I want to go over here. So first of all, I have this plate here for the Arduino to sit. I have these cutouts for the power and the USB source. Over here, I have the slots for the cuvettes to slide into. So there's 3 slots for the 3 different LED colors. So the LEDs themselves will slide into these circular cutouts here. And then on the other side of this section, I have these square cutouts for the photodiodes to sit. So this should offer a pretty good containment for everything. So what I need to do now is to go try to get this printed off and see how everything fits. Alright, so this just finished printing, so I went ahead and I put the Arduino in there just to make sure that everything's going to fit. It seems like it fits in there pretty snug, everything lines up. All of the other components seem to be spaced out pretty well, especially this cuvette section. The cuvette slides in, very nice, stays put just how I need it. So there's a few other tweaks, small things that are going to be fixed and done onto it in other versions. But for right now, I think that this is going to work, and I think that we can go ahead and get some stuff put in here. So I went ahead and wired up the red LED and one of the photodiodes just to do a simple little test and see if everything is working on the electronic side and the code side. And from what you can see, it seems like it's all working. So I think from here, it's time to go ahead and get all of this put in here permanently. Since all components needed to be connected to a common ground, my solution here was to just connect them all to a perf board. This is definitely not the best or potentially even the safest method, but for the sake of the prototyping, it'll work. At this point, the colorimeter is practically finished. After fitting all of the components in, I printed off a couple extra pieces just to tie this together. Firstly, I have a lid that's covering all of the components and just makes everything look nice and neat. And then I have a little light shield to cover the cuvettes, and this just helps reduce that light interference. So now I can start thinking about what I actually want to measure in my water samples. So as I mentioned, colorimeters can measure a wide range of constituents, so this is what makes them so versatile. So the first thing that comes to my mind with this river water is to measure nitrogen. So nitrogen is something that's input from farming and agriculture, which has extensive presence around this area. Unfortunately, the chemical process for actually preparing the samples to measure nitrogen is pretty tedious and involves some fairly expensive chemicals. So this would set the price tag well over a few $100s just for chemicals alone. To keep this project cheap and simple, I decided to measure something else, something called tannins. So tannins are naturally occurring polyphenolic compounds that occur in most plant species, especially evergreens, which are very prominent around this area. So when the plants die and decay, these tannins dissolve and work their way into the water, which is what gives that water somewhat of a brown tea looking color. So calibrating this device to measure tannins as opposed to nitrogen species, it's much cheaper and much simpler, which is better suited for the scope of this project. The procedure is actually pretty cool. When ferric chloride comes in contact with tannic acid, iron tannate complexes begin to form. This iron tannate is dark blue or black in color, allowing it to be used as an indicator for tannins. Before I can just measure tannins in this river water, I need to actually calibrate this device to be able to measure tannins. And that involves making a few standard solutions of known concentrations of tannic acid and running them through the device to create a calibration curve. So the next step I need to do now is to prepare these standard solutions and run the calibration. Now the two chemicals I need to do this, tannic acid and ferric chloride, can be found online for pretty decent prices. To prepare these standards, I first need to mix up a stock solution of tannic acid that the other more diluted standards will be made from. This is made by mixing 1 liter of DI water with 1,000 milligrams of tannic acid, creating a 1,000 milligrams per liter concentration stock solution. Once the stock solution has been prepared, I'll carefully measure specific ratios of stock to DI water to create the other multiple standards of different diluted concentrations. For example, this standard contains 2.5 grams stock and 47.5 grams of DI water, and this gives me a concentration of 50 milligrams per liter. Now you'll notice with the prepared standards that there is very little color variation between the 0 milligrams per liter, which is called the blank, and the full stock solution, which is 1,000 milligrams per liter. The colorimeter would not be able to pick up these minute differences alone, and this is where the ferric chloride comes into play. The ferric chloride is first diluted in DI water because it comes in a very concentrated form. In this case, I mix 1 gram of ferric chloride with 100 grams of DI water. After this solution is made, I'll mix 3 grams of it to 30 grams of each of the tannic acid standards. This should start forming iron tannate complexes, as we can see here, and at this point, the standards are ready for calibration. So I ended up cutting the final standards down to try to achieve better accuracy within a lower concentration range. So I ended up with 0 milligrams per liter, the blank, 12.5 milligrams per liter, 50 milligrams per liter, 100 milligrams per liter, 150 milligrams per liter, and then lastly, 200 milligrams per liter. So side by side, you can tell that the color gradient is much more pronounced, and the colorimeter should definitely be able to pick up discrepancies between these. So to run the calibration, I created a very basic script within the main graphic user interface, which I have not shown here yet. So in the graphic user interface, which is seen here now, I can go to Calibration. This will open a separate window. In this separate window, I have the control over my calibration. So I can firstly choose what parameter I want to test for. So in this case, I'm testing for tannins. I can secondly choose the number of standards that I'm using. So I have 6 standards. I'll input that. After this, I can simply click Start Calibration. So this opens up a window to enter the concentration for my first standard. So my first one is probably going to be my blank. So that is 0 milligrams per liter. Once I click OK, it will prompt me to go ahead and input that cuvette with the sample into the device and to go ahead and measure it. So clicking OK will start the measurement. So this will run for about 15 seconds and take an average of those 15 measurements taken once per second. So I'll go ahead and do this for all 6 samples, and then we can discuss the results. So I am happy to confirm that the calibration was a success. In the results here, we can see that we got a high R squared of 0.99, as well as a relatively low mean average error of 4.07 milligrams per liter. Now for a first version of this isn't that bad, and it is completely reasonable to suspect that I can get this mean average error down to as low as potentially 1 milligram per liter with further versions. But that'll be saved for another video. With this level of accuracy achieved, I think that I'm ready to go ahead and collect that water sample from the river and test this out in a real-world scenario. After a quick walk down the greenway, I found this absolutely lovely place to collect my sample from. With these samples, the first thing I needed to do was to filter them to remove any suspended sediments, after which they were prepared the same exact way as the other standards by adding in ferric chloride solution. So what I have here is one of the final prepared river samples, and you may notice something about it that's a little different than the standard solutions, and that is that it is yellow. We should have expected this to turn some sort of blue-black color, as we saw earlier, indicating that there are iron tannate complexes forming. So what's happening here? So I have two hypotheses as to why this is happening. The first of which is that there are just no tannins in these river water samples to form these iron tannate complexes, which is why it's taken on the same yellow color as the ferric chloride. Now, the problem with this is that my standard solutions, especially the blank, the one that is 0 milligrams per liter, did not turn this same yellow color. It was, for the most part, clear. So this tells me that maybe something else is going on. The second, and possibly more likely hypothesis, is that the presence of other organics, such as humic substances, are essentially stealing the iron from the ferric chloride, and this is preventing that iron from binding the tannins. Either way, when I ran these samples through the colorimeter, I got two different readings. First one was 6 milligrams per liter, the second was 7 milligrams per liter. So this is still pretty close to zero and could be the result of a combined effect of this yellow discoloration altering the absorbance, as well as that 4 milligrams per liter error associated with this calibration curve. While this conclusion is a little bit disappointing, the main conclusion, and more important one, is that the colorimeter works. We've also established that it can be built for much cheaper than other typical devices can, and we've also seen that it can calibrate to a relatively high degree of accuracy. The biggest expense here was, of course, the calibration materials, which can vary between different constituents, but this is also probably the core reason why these multifunctional colorimeter devices can be so expensive. That being said, I have a long list of upgrades that I would really like to implement for the next version. Some of these include redesigning the housing for better aesthetic, redesigning the circuitry and making things more simplistic and more reliable, and then of course, I'd like to calibrate for more constituents and just see how many different things this device can be calibrated to measure. So if you thought this video was interesting or you learned something new, give it a like. Let me know that you want to see part 2. And always feel free to leave a comment, give me suggestions on things that I can improve for the next version. And remember, stay inquisitive.